Hello and welcome to Mr. Linford's math course. In today's presentation, we're going to be talking about the application of linear equations into variables. In particular, we're going to look at application problems that require us to interpret linear equations, actually come up with and write linear models, or in particular linear equations, for a described situation, as well as write linear equations and linear models for different data that we are given. So starting off, I'm going to have us walk through a problem together. This problem is one that talks about different leaves, different types of leaves that are out there. And I'm just going to kind of explain really quick what the general idea is. There are a couple types of leaves. There are smooth leaves and there are toothed edge leaves. So what they categorize in this study as smooth leaves are really leaves that have nice smooth edges to them, okay? That's just a regular, typical kind of smoothed edge leaf, as opposed to a toothed edge leaves, which are more jagged. I'm thinking of like oak trees, maple trees, stuff like that, stuff that has jagged edges to it. You can tell I'm an amazing artist, so obviously this should all make sense to you. What the study found was that there is a correlation or a relationship between the average temperature, the average annual temperature of an area, and how many smooth leaves there are. So what they're saying is, okay, imagine you are an environmental scientist and you go out into an area. Maybe you find 1 square mile. And you go in that area and you survey all of the trees that are in that area. You get a team of people and you survey all the different trees that are in that area. You could figure out what percentage of the total trees have smoothed edge leaves. So you could figure out what is the percent of smoothed edged leaves in the area, okay? Knowing that, you would also be able to come up with what the temperature is. And that's what people did here when they came up with this. They plotted all these different percentages and temperatures, and they came up with this really nicely linear graph. It's a very linear graph that describes, based on these, how many smoothed edge leaves you found. These are all percentages. And whatever the percent of the smoothed edge leaves you found, you can tell what the temperature is. Now, for some reason, when I uploaded this image, the equation didn't get printed, but there is an equation for this. They found that the equation is y equals 0.3006x plus 1.141. So that's the equation that models this line of best fit. Let's think about what this equation means. Here I'm telling you x represents the percentage. X is the percentage of smoothed edge leaves, right? So maybe you go into an area and you find that half of all of the trees has smooth edged leaves. So 50% of the trees have smooth leaves. Then the y-axis is going to represent temperature. Y represents the temperature. So we can see as the percent of smoothed edge leaves increases, so does the temperature. Now that we have this kind of idea that, smoothed edge leaves tend to grow in warmer climates and toothed edge leaves tend to grow in cooler climates, let's try to interpret what all this information is telling us. The first question I ask is to tell me what the slope of our linear model is. I want to look at this linear equation right here, and I want to know what's its slope. Okay, a lot of times students will go and they'll try to find, hey, maybe that point passes through the line and maybe this point, and we could potentially, use the slope formula to figure out what they are. We can kind of approximate what their coordinate points are. And I'm always a little surprised when students do that because I often say to them, hey, look at the equation. Aren't you given slope? That's the slope right there. It's 0.3006. So let me move over to the next page so I have some room. And so for the first part here, what's the slope? Well, that slope's just going to be 0.3006. Now what I ask you to do is interpret the slope in the context of this problem. What I mean by this is let's put some words to it. Let's describe what this slope means. Before we do that, I always like to write slope as a fraction. Even if I have a decimal, I like to put it over 1. And I also like to include some units on this. Remember, slope is the change in y over the change in x. So the change in y, that was our change in temperature. And the change in x, that's our change in percentage. So what does this slope mean for this problem? Meaning, describe it in units to me. So what we would say here is, for 1% increase in smooth leaves, the temperature goes up 0.3006 degrees Celsius. It goes up roughly 1/3 of a degree Celsius. That's all that this implies. If I increase 1% of my smoothed edge leaves, then my temperature goes up roughly 1/3 of a degree. That's all I mean when I say interpret it for the context of the problem. Meaning, don't just tell me that the slope is 0.3006. In a math class, okay, that makes sense to me. I can picture what's going on with the graph. But maybe the scientist is saying, hey, that doesn't help me describe the relationship that we're seeing between the variables, the relationship that we're seeing between the percent of smooth leaves and the temperature. Now, the next part, I want us to figure out what's the y-intercept. Now, some people would say, hey, wait a minute, Linford, the graph doesn't even hit the y-axis, so what should we do? And again, just notice, if you look at the equation, I give you the y-intercept. It's right there. So go ahead and just use that one. It's 1.141. So that y-intercept is going to be 1.141. And now we have to interpret it for the problem as well. Let's think, what does this y-intercept mean for my specific problem? To do this, let's rewrite this as an ordered pair. Let's write it as the coordinate point, 0 and 1.141. So there's the ordered pair. That's where I cross the y-axis, right? Again, let's put some units on this. These are my x's, so that's percent. This is my y, so that's degrees Celsius. So what does this mean when x is 0 and y is 1.141? Pause the video, take a minute, think to yourself or with a partner, what does this mean for my problem? Okay, the big idea here with the y-intercept is we're saying for 0% of smooth leaves. So if I found no smoothed edge leaves, the temperature is about 1.141 degrees Celsius. That's all that that's saying. For 0% of smooth leaves, I should have about 1.141 degrees Celsius. And does that make sense? Well, actually, it kind of should make sense because 1.141 degrees Celsius, that's about freezing. Do you expect any leaves, any smooth edge leaves to be left on their trees after, you're about at 1 degree Celsius? Well, no, you're in winter pretty much. So we really shouldn't have any population of smooth leaves. The last part we're going to talk about for this problem is using this model to approximate the temperature of an area if you know the percent of leaves. So the model was y equals 0.3006 x plus 1.141. Now we've gone out into an area and we've measured and computed that the total percentage of smoothed edge leaves, well, 80% of all the leaves were smooth, okay? So what's the temperature? Again, just remember your units. X controlled the percentage, so I'm going to plug in 80% for X. So y equals 0.3006 times 80 plus 1.141. Okay, quick side note. Typically, we would never plug in 80 as my percentage. We would plug in 0.80. However, when the equation was built, it was done in such a way that you can just plug in the number 80, okay? So don't worry about, in this problem, turning the 80 into 0.8. Just plug in 80. However, going forward, any problem you do in my class dealing with percent, you always want to work with the decimal version of it, okay? So that's just a quick explanation, some side information that you needed to know. So we're going to take that 80 and we're going to multiply it by 0.3006. And then we're going to add 1.141. And we should get something about 25.189 degrees Celsius. So for 80% of all the leaves to be smooth, the temperature should be roughly around 25 degrees Celsius. And if I'm converting right in my head, that should be somewhere in the 70s, I think, which is a pretty warm area if the annual temperature is in the mid-70s. Okay, here's what we're going to do. We're going to take some time to work on writing a linear model from described information. In this problem, we're talking about a tree. Trees grow throughout a given year. Due to the way that they grow during the different seasons and weather patterns, a tree will produce a ring. And each ring takes about a year to produce. This allows us to determine the age of trees. That's why we sometimes count rings, and we can approximate the age because a ring takes roughly about a year to produce. So let's assume you bought a tree that has a 76 millimeter radius. So if I had a tree and I cut it in half, and I look at its trunk, and I look at what I've just cut, I would say that the radius, which is from the center of the circle out, is 76 millimeters. And every year that it grows, let me get a bigger drawing. Here's the image. And here's the radius of 76. And every year, it grows a ring. And these rings are typically about the same size. It would be 1.75 millimeters. And then we get another one that's 1.75 millimeters. And we keep doing that. And we're going to assume that the tree grows in average weather patterns, so we typically have same-sized rings. What I want you to do for this particular problem is to first write an equation to figure out what the total radius is of the tree. So y is going to be my total radius for x years. So let's write an equation for x number of years to tell us what y, the total radius, is going to be. Pause the video, take a couple minutes to work on this, and then we'll come back and explore. Okay, so let's get a clear work area, because what we want to do is come up with how we might go about writing the equation. Now, I need a y equals mx plus b. Y is going to be the radius, and x is going to be the years. So let's think about this. Every year, how much do I change in diameter? What's my rate of change? Well, I add 1 3/4 millimeters every year with a tree ring. So let's see, that might be my slope, 1.75. Yeah, that should be my slope. So for every year, I would have 1.75 added onto it. So 1.75 times x. But be careful, our tree started at 76 millimeters already. So the radius of my tree is 76 millimeters from when it started, plus 1.75 for every year I've had it. There we go. That's our linear model. Y equals 1.75x plus 76. Now let's try to use this model. Let's figure out what would the radius of the tree be after 5 years. So remember, what are our units? X controls the number of years. So if I know it's been 5 years, y equals 1.75 times 5 plus 76. Okay, let's see what we get here. 1.75 times 5 is 8.75. And then plus 76, that's 84.75 millimeters. Those are the units that we're in. So there, I've just figured out what that radius is going to be. Now, let's try to figure out if I know what the radius is, could I tell how many years it's been? So let me say that the radius of a tree trunk is 104 millimeters. I want to figure out how long I would have had that tree, or how long it would take that tree to get to this radius. So I just have to solve for x. So take 104 and subtract 76 from it to get 28, then divide by 1.75. So x should equal 16 years. If I want this tree to get up to a radius of 104 millimeters, it's going to take about 16 years to do so. So again, when we go about evaluating stuff, you have to be careful. What are the units, okay? X represents what, and what does Y represent? Now let's try to look at how we can go about writing a model or creating a model from observed data points. So in a particular study, the size of a tree was found to impact the absorption of carbon dioxide, how much it could absorb. Now, the larger the tree, the more effective it is at absorbing carbon dioxide. And in particular, what they found, because trees tend to, their height tends to level off, and they tend to stop growing in height after a certain while. But then they notice that the trees tend to, after they grow fairly tall, then they start growing thicker with more branches, and then they start growing more horizontally. So the larger a tree gets, whether it's vertically or horizontally, it will be able to absorb more carbon dioxide. So we're going to estimate that we got an oak tree, and it is a 14-foot tree, and it absorbs 15 pounds of carbon dioxide a year. And this corresponds to the ordered pair, and I know for some reason it didn't get copied down in the text, but this would be the ordered pair 14, 15. So for a 14-foot tree, it can take in about 15 pounds of carbon dioxide. So for a 30-foot tree, it could take in 23 pounds of carbon dioxide. So that ordered pair, 30 and 23. So what we want to do is go ahead and write a linear model that goes through these two ordered pairs. What I want you to do is pause the video, take some time, create this model, and see if we can answer some questions about it. Okay, this problem, very straightforward because it's just writing an equation of a line through 2 points. So we first need to find the slope. We can say that's 23 minus 15 over 30 minus 14. This is just going to be the slope formula. So let's see, 23 minus 15, that should be about 8 over 16, which is a half. So the slope here is a half, and then let's figure out what the y-intercept is. So y equals 1/2 x plus b. So then, why don't I plug in a point? So 15 equals 1/2 times 14 plus b. So that's 7 plus b equals 15. Subtract 7. 8 equals b. Here's my equation. Y equals 1/2 x plus 8. We have done nothing new. Nothing new. All we did was we said, hey, here are these two ordered pairs. Let's go ahead and write an equation of a line through them. Okay? Now, what is the slope of the line? Well, we just said it's a half. But what does it mean in the context of the problem? We said before, try to put some units on slope. X represents the feet. How large the tree is. And Y represents the pounds of carbon dioxide that are getting absorbed. So in this problem, the slope means for every 2 feet, that the tree grows, it can absorb 1 pound. My stylus is messing up, sorry about that. So for every 2 feet a tree grows, it can absorb 1 pound of CO2. That's what that slope says for this particular problem. Now, the other problem I ask you is to go ahead and try to use this to figure out what the amount of carbon dioxide, how much carbon dioxide could be absorbed for an 80-foot oak tree. So we have y equals 1/2 x, and I've already forgotten the equation, plus 8. Okay. So what we need to do is say, okay, I got an 80-foot oak tree. How much carbon dioxide can it absorb? Well, thinking back to our units, x controlled the feet. So let's plug in 80 for x. So 1/2 of 80 is 40, plus 8 is 48. And we could write this as an ordered pair, 80, 48. But that's the big idea with these problems. When we say interpret and then evaluate, we just want to be very careful with the units that we're using here, okay? So that's it for me. If you have any questions on this video or comments, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video, if you have any questions or comments on the content, and until next time, take care.